Voyager 2. Like Voyager 1 before it, it is a marvel of technology, a remarkable instrument of humanity's search for celestial knowledge. Late in August 1981, 4 years out from Earth, Voyager 2 reached that most beautiful of planets, Saturn. The first of the two Voyagers had flown by Saturn in November 1980, sending spectacular close-up pictures 140,000 million kilometers back to Earth. Voyager 1 discovered hundreds of rings, all very different. Voyager 2 would fly even closer to Saturn and its moons. Its mission? To expand upon the revelations of Voyager 1. The flight of the Voyagers is an ongoing project with several major assignments in future years. Their control center is the Jet Propulsion Laboratory in Pasadena, California. Scores of reporters came there from all over the world for the week of Voyager 2's Saturn encounter. They reflected an excitement over the space probe that was as strong among ordinary people as among scientists.
For a long time trying to explain.
And they followed Voyager's progress at daily press briefings in a packed auditorium. On August 24th, the day before the flyby, reporters saw a movie made from stills Voyager took on its approach of mysterious spokes in Saturn's wide B ring.
The time-lapse sequence has now been put
Dr.
together.
Brad Smith, head of the team assigned to interpret Voyager pictures, described the film.
Less than an hour ago, and there's a lot going on in this time-lapse sequence. I feel that the spokes are trying to tell us something, although it may be days or weeks before we really understand just what they are trying to tell us. By that time, you'd all be gone, so we're going to share it with you this morning, and all of you out there can do instant science right along with the rest of us in trying to see what's happening. There's a lot of complex activity going on. One tends to see some spokes looking as though they're shearing out, others seem to be forming, others seem to be fading away, so why don't we just go to it and we can all analyze the spoke problem. Go through it twice fairly fast, and then twice a little more slowly. You have to be careful of projection effects, but it appears that some of the features actually sharpen. It really
Dr.
is
Smith also
something.
showed a new and spectacular color picture of the rings.
Now, this is greatly exaggerated color, but what we were concerned about were these changes within the B ring. When you look at a normal color version of the B ring, it looks fairly uniform. But when you really push and particularly get down into the ultraviolet, then we see that these are real changes across the B ring. So here's the C ring looking blue relative to the other rings. It's a little bit dark, but the Cassini looking relatively blue. And then this structure here, where this region is a little bit bluer and this is a little bit redder than average. So even within the B ring, there are differences in the spectral reflectivity. It is not a homogeneous ring in that sense.
Each day in the laboratory's own television production, mission scientists were interviewed by the voice of mission control, Dr. Al HIBBS. HIBBS asked Dr. Smith about those color variations in the rings.
What are the possibilities that could account for this kind of difference? Does it imply these are quite different minerals, or they've been exposed to different kinds of things?
Well, that's what we don't really understand. All we see is a surface effect. It could mean different composition among the particles between the B ring and C ring, or it could be a purely superficial effect. Something happens to the ring particles, perhaps color dislocations in the crystal structure that due to high energy particle bombardment slightly colors the surface of the particles different in the two ring systems.
Smith and his fellow scientists were sure of one thing.
Now, in our counting of rings in Voyager 1, we had estimated that there were hundreds, perhaps even up to 1,000. Now we're getting higher resolution, and we're finding that many of the rings that were seen that thought were single rings in the Voyager 1 photography are now turning out to be multiple. In some cases, 30 tiny individual ringlets where we thought there was only one. So what we're finding is that we shouldn't be saying 1,000, we should be saying thousands. There is far more structure there than we thought from the Voyager 1 photography.
Dr. Smith admitted a disappointment. Voyager 1 had discovered 3 new Saturnian satellites. 2 of them seemed to keep the thin outer F-ring contained, like sheepdogs chasing strays back into the pack. This led to a theory that the gaps between various Saturnian rings were kept clear by other satellites. But unfortunately, Dr. Smith told HIBBS no new satellites were being found.
To explain.
And now, after searching, then here, supposedly it would be located in some portion of this particular the dark gaps on the top and bottom of that close-up section.
In fact, it was within those 2 dark gaps that we conducted the search for this 30-kilometer object. Unfortunately, we didn't find one, and that leaves us unable, at the moment anyway, to explain the mechanism that creates these wide gaps. It was the only good theory we had at the time, and it's gone down the tubes now. Yes.
I hope another theory comes up.
August 25, 1981. At last, after 4 years, the day of Voyager 2's closest approach to our second-largest planet. At dawn, California time, the spacecraft was still about 800,000 kilometers away. That evening, at exactly 8:25, Voyager would fly over Saturn's cloud tops and begin its long swing around the dark side. By now, scientists had had a chance to examine Voyager 2's pictures of the moon Hyperion, the Saturnian satellite that's an American discovery. The first picture of the moon, as it turned out, was of its flat edge and suggested a cylindrical shape. But later pictures showed an odd flat shape akin to a potato, a peanut, a hamburger patty. And while the axes of other Saturnian moons are in line with the axis of the mother planet, Hyperion's is tilted the other way. The scientists couldn't tell why. Voyager had taken time-lapsed pictures of Saturn earlier in its approach. A film made from these pictures showed new information on Saturn's weather. Dr. Edward Stone, Voyager project scientist, explained that scientists were looking for rotating cyclone-like storm systems in Saturn's northern hemisphere.
Sure enough, we have found them. We found them spinning off behind a larger structure, and it's those storm systems which evidently are very important to understanding the development of the weather system on Saturn and presumably also on Jupiter. So I think that major objective, once we do the detailed analysis of those storm systems, exactly how rapidly they're rotating, what their speeds are, and relate those to the high-speed jet streams, that we may have a very important piece of the story for the weather system on Saturn.
The hours ticked away, and Voyager raced on towards Saturn, as this animated film dramatically illustrates. The pull of the planet's gravity steadily increased the speed of the spacecraft. When the day began, Voyager was traveling at 13.5 kilometers per second. At closest approach, it would be moving nearly twice as fast, or more than 24 kilometers per second. During the last 2.5 hours before closest approach, Voyager performed a fascinating ring count task. Some 2 hours of watching the star Delta Scorpio through the rings. The number and length of the light flashes would disclose precisely how many rings there are, as well as their positions and widths. Voyager then moved to its closest approach. Flying 100,000 kilometers above the cloud tops, the spacecraft entered the planet's shadow. Earth and Sun disappeared from its view. Voyager's radio voice was cut off by the planet. It would be heard again, if all went well, when the spacecraft emerged from the shadow. But scientists would have to wait more than an hour for renewed Voyager transmissions to reach Earth and receiving stations in Australia, if all had gone according to plan.
The Australian station reporting into the Deep Space Control Center the status and operations of that station as it picked up the signal as it came through, and all is well.
Champagne was poured in celebration. Project manager Esker Davis was happy.
Hey!
After its long journey, Voyager 2 had been off target at closest approach by only 2.7 seconds and 48 kilometers.
The SEM synthesizer frequency for station.
But suddenly, scientists on duty discovered that something was wrong. Voyager was telling them it had problems. What the scientists discovered was that the scan platform, which holds the cameras, would not move.
Track 243, all interfaces are up again.
Next morning, August 26, with Voyager moving on past Saturn, Esker Davis demonstrated the problem for reporters.
This whole thing is the scan platform that we're dealing with. It moves in two directions. This is the azimuth direction, and that's the direction of rotation where we're having a problem, where it appeared to get stuck during the occultation time period. It also moves in elevation, and that direction appears to move without any difficulty and move properly. So we are investigating with these tests the movement of the scan platform. A test last evening moved it a very slight bit to see if we could move it. Tests earlier this morning, we're increasing this amount of movement, this excursion. And the gearbox that drives all of this is this device, odd-shaped looking area here, where all of the gearboxes, it's a bit of clockworks kind of thing, a lot of gears, and drives the scan platform through this series of pipes and axes.
Speculation was that Voyager had flown through a swarm of small electrified particles that fouled its gears.
The optical navigation becomes very powerful.
Dr. Stone was asked how much the cameras had missed after being put out of action.
And therefore, the really new part of Voyager 2, that is imaging of the right side of the rings at very close approach, has been completed. The part which we will miss, obviously, is imaging of the dark side of the ring. And of course, that's unfortunate, but we did do some dark side, quite a bit dark side imaging of the ring on Voyager 1.
The platform doesn't come back, and the spacecraft can't be oriented for one reason or another. Can you put a percentage number on how much of the mission goals have been achieved?
I would have to say essentially all of them. I think the major area where we're missing some key data is probably on Enceladus, having gotten only one of our 3 high-resolution mosaics, and on Tethys, where we got 1 of 2.
Meanwhile, Voyager had continued to send back pictures taken before the closest approach and stored for later transmission. One such picture concerned that thin outer F ring. This Voyager 1 picture had made it seem like several rings braided together. Dr. Stone discussed the new Voyager 2 F-ring picture with Al HIBBS.
And the F-ring in this picture, and this is one of the things that surprised us, does not show this beautiful braided structure.
Well, you remember that on Voyager 1 we had just one image where that was a very braided structure. It may turn out that that is not a characteristic of the entire ring, but is a very localized effect. And so we will need to, we're imaging a great deal more of the F-ring to try to trace out its characteristics.
Here's another one of that same region. And then here we're getting, again, the detailed structure of the ring system themselves.
Yes, some of these, like that one, where one can see between you can see the narrow, dark gap, and next to it a series of shallower, less dark ridges, if you like. Evidently, there are variations in the thickness of the ring. We're looking at the light scattered off the lighted side of the ring, and that's, again, telling us something very important about how that gap is formed. I'm sure it's telling us something of that nature.
August 27. By day's end, Voyager 2 would be nearly 2.5 million kilometers past Saturn, cruising around 12 kilometers per second.
Specified.
The word from project manager Esker Davis was that the scan platform had been made to move, but not as much as he'd like.
So we cannot yet say we can move it reliably and that we've restored some kind of normal operation. So that's still our objective. We're not yet at a place where we're saying we're fixing the problem. We're still trying to define the problem and understand what it is. There are going to be a lot of tests, as I said, over the next few days. A bit upbeat and positive, but a lot of work to do yet to get it where we want to be.
Good morning. Yesterday, I got the question, given that the scan platform had stopped, what was my estimate of our percentage of success for the Voyager 2 encounter? And I did not really have a quantitative estimate at that time. Well, I've had 24 hours since then to give the question some thought, and I have a number for you. The number is 200%.
At the same press conference, a dramatic partial picture of the moon Tethys was shown. The heavily cratered moon was to be photographed soon after the spacecraft flew around behind Saturn. Voyager managed to get the partial picture in spite of its jammed platform. Even more interesting were the pictures of Enceladus, brightest moon in the solar system, with a surface so starkly white that it radiates 100% of all the sunlight that falls on it. Voyager 2 had sent back Enceladus pictures taken just about the time of its closest approach to Saturn, just before its scan platform jammed. Enceladus has stayed white by washing itself clean. Dr. Eugene Shoemaker explained.
It turns out there's a region along the satellite here which was intensely heated about 3 billion years ago, allowing most of the craters to relax, while at the same time in this region over here, the craters are not relaxed. So that we discovered, quite unexpectedly, that the satellite was heated non-uniformly.
Like Earth and its moon, Enceladus and neighboring Dione pull each other back and forth each time they pass, creating tides and heat.
This may be a clue as to how the tidal heating takes place. It may take place when there's a sudden rupture of the satellite, perhaps by impact, allowing rubbing of the two different parts of the satellite, frictional heating under the tides, and then a discrete region will be warmed up and actually may become liquid in the interior, because we think that some of these surfaces actually have had water flowing out on the surface, and the crust then becomes very soft, and the craters will collapse.
August 28. Voyager 2 was 3 million kilometers beyond Saturn. With luck, there still might be pictures of the planet's dark side. Meanwhile, this was the last official day of the encounter. When it was over, reporters would pack up and go home. The final morning press conference began with good news.
Come a little smile on my face today, because there's a good chance that Saturn will be on our TV screens by the end of the day.
The bearer of the news was Richard Lesser, Deputy Project Manager.
Progressively, in each of the 3 diagnostic tests we've performed on the scan platform, the stickiness and the slower than normal performance that we've seen has gotten better. The tentative conclusion, and this isn't a whole lot of data to work from, is that the platform gets better with use after our initial problem.
A few hours later, there was indeed a Saturn picture on the screen. Dr. Stone and Al HIBBS discussed it in their daily interview.
This into perspective, but I think to start with, we ought to point out we have a picture, finally, from the Voyager. It doesn't look like much to begin with. This picture is part of a sequence which was deliberately underexposed, aimed at a portion of the dark side of the rings, and indeed the dark side of the rings is right in the middle of the picture.
Yes, we see the shadow of Saturn cast on the rings, and of course we're looking at the dark side of the rings as well, so the rings are not very bright even where they're not behind Saturn. This is a wide-angle camera shot and is an indication that, in fact, we did successfully reorient the scan platform and will allow us to continue observing Saturn for the next few days. It's really quite an exciting picture to see.
Elsewhere at the laboratory, scientists were finding new surprises in their immense treasure of incoming data. One concerned that thin F ring, which seemed to keep changing. In the latest pictures, it was not a braided ring, as Voyager 1 had seen it, not a single strand, as Voyager 2 had seen it earlier in the week, but many strands. An interesting theory about the black spot on the leading edge of Iapetus came from an Australian scientist. Voyager 2 had learned that Iapetus has less mass than had been predicted. That could mean, the scientist suggested, that the moon contains methane along with its ice and rock. Solar radiation and other particles bombarding the surface could react with the methane and form black-as-pitch hydrocarbons. And now there were second or third thoughts about the possibility of additional shepherding satellites. They were in favor again. The new theory centered around the kinked rings in the Encke division, named for its founder. Doctors Richard Terrell and Jeffrey Cuzzy were two scientists who helped interpret Voyager's pictures.
Well, at least for this ringlet, we call it the kinky Encke. The kinky in the Encke. Now, I'd say these kinks here are a pretty good fit to the same theory that's been advanced to explain the braids in the F ring, which basically involves gravitational pulls by close-in shepherding satellites. And this might be taken as an indication that this division contains some such small shepherding movements, that is, an embedded movement of a sort. It would probably have to be pretty small. We'd never be able to see it because these braids, these kinks are so close together.
Small meaning maybe a mile in diameter, so.
Voyager 1 had found rings in the Cassini division, once thought to be a gap. Voyager 2 was finding more.
Before we had the idea of the Cassini division being a division, and then we saw it close up and we saw, okay, it's really a bunch of rings bracketed by two divisions, smaller divisions. Now we're looking at each one of these divisions, and they're not even simple divisions. They've got rings inside them, and those rings have complicated structure.
When asked for their final analysis of Saturn's ring system, Terrell and Cuzzy said there is no final analysis.
I think a lot of people were sort of under the impression as we get higher and higher resolution on the rings, we'll all of a sudden reach the point where we'll say, aha, we found it, this is what explains the structure and the things. I think what we're finding when we get higher and higher resolution, the theories that we develop to understand the rings are getting more and more complicated, just as the structure in the rings are becoming more complex. I'm trying to get a deep understanding right now from more or less the first look data. I mean, there's an overwhelming amount of data, even with the problems we had in the second half of the encounter. It's sort of like drinking out of a fire hose. There's so much data coming at you so fast that you can't really formulate your theories in that short a time scale.
One scientist advanced a new theory to explain the different colors in the rings. Color, he suggested, is determined by particle size. The smallest are nearest the planet, the largest at the outer edge. But he said the composition of all the particles seems to be the same. Thus he sided with those who believe that all the ring material came from a single celestial body that broke apart. Dr. Brad Smith talked about the possibility of following up on the new ring data.
We hope that we've obtained the right observations now with Voyager 2. But if we haven't, we still have another chance. When the Space Telescope goes into orbit around the Earth in 1985, it has sufficient resolution to reveal these spokes at the level at which we need to study them. That, unfortunately, is about the only phenomenon going on within the rings where future ground-based observations or near-Earth observations will help us out.
With Voyager 2's Saturn flyby, as with Voyager 1's, there were remarkable photographs that went beyond science to the aesthetic wonders of the distant heavens. Dr. Stone, highly pleased with the Saturn encounter, looked ahead to what he hoped would be a long life and more exciting discoveries for the last of the Voyagers.
Well, Voyager 2 is now on its way to Uranus. It arrives at Uranus in January of 1986. Uranus is about half the size of Saturn, but still a giant planet compared to the inner planets, one of which we live on. Very interesting thing about Uranus, though, is that its spin axis will be pointing basically at the sun when we arrive in 1986, so that as we approach Uranus, we will see the North Pole, and we'll see in the sky a bullseye pattern of 9 narrow rings and the 5 known satellites orbiting in the same bullseye pattern. We will fly by Uranus, returning data with quality comparable to that which we achieved just in the last week at Saturn, head on to Neptune, which is 30 times as far from the sun as the Earth, encountering Neptune in August of 1989. And we have a plan to essentially fly right over the top of Neptune's North Pole, the closest planetary flyby of the whole mission, on to its moon Triton, which may be a twin of the moon Titan at Saturn.
Remarkably, with that 1989 flyby of Neptune, American spacecraft will have closely investigated every planet of our solar system except Pluto. There have been no missions to that farthest of planets. But scientists believe Neptune's moon Triton is so similar to Pluto that much will be learned after all. Both Voyagers will continue operating until their fuel runs out near the turn of the century. When that happens, their antennas will begin to drift and lose contact with Earth. Before that time, Voyager 1 should find the edge of our solar system, where our solar wind is replaced by intergalactic winds. With their missions accomplished, the 2 Voyagers will have just begun an infinite journey.